We're going to assume that our spring has a ball or a box on the end and look at some possible states. So the spring has a natural resting position, which is called equilibrium. And in that case, we'll assume that the x is equal to 0. The ball is sitting right at x equals 0 on the x-axis. We can compress the spring, by pushing it inward. In that case, the ball will be at a negative number, pushing the spring in. We could also stretch the spring out. And if we did that, we'd be looking at pulling the string forward. In this case, the x location of this object at the end of the spring would be a positive x value. Now, different springs are going to have different physical properties. Some springs are just springier than others, and some are stiff. Like, think about the difference between the springs in your mattress and the spring on a door jamb. And so each spring has a constant called spring constant. We're going to call that K, or constant. From physics, there's something called Hooke's law, which says from an equilibrium position to x is given by big F of x equal to K times x, where K is the spring constant we just discussed. We can use this fact to determine how much work is being done on a spring to move it from one place to another. So suppose we know it takes a force of 50 newtons in the negative direction to compress a spring 0.1 meters from equilibrium. How much work is done to stretch the spring 0.5 meters from the equilibrium position? So the first thing we want to do is find the spring constant, a value of K that tells us the physical properties of the spring. So here we know that 50 newtons is equal to K times 0.1 meters. So we would have that K is equal to 50 newtons divided by 0.1 meters, which would give us K is equal to 500. Now, we're not done. That's just the first step, but we have now found the spring constant. Next, we need to apply the spring constant into the integral. So now, based on this work in step 1, we know that the variable force we're working with here is f of x equals 500 times x. And so we're going to take that and look at the integral from 0 to 0.5, 500x dx. That's what we need to evaluate. So now this should be an integral we're familiar with at this point. In evaluating this definite integral from 0 to 0.5, 500x dx, I find an antiderivative I can use, which will be 1/2 times 500x squared. So I can plug that in here. I can plug in 1/2 times 500 times 0.5 squared minus 1/2 times 500 times 0 squared. And again, this 0 just cancels out. So this will become 1/2 times 500 times 0.5 squared. And this is the amount of work done to move this spring. It's really helpful here to draw our diagram and to remember that if the natural length here is 20, then the equilibrium position is still at x equals 0. So when we're stretching the spring out to 25, we're going to x equals 5. Now here we're going to find the spring constant. But we're told the work. We're told the work that it takes to expand this. So we're actually going to be looking for the integral from 0 to 5 of our kx dx. And we know that that's equal to 3 joules. So I don't know what the k is yet. What I'm going to have here is that my antiderivative is k over 2 x squared. And I can plug the bounds in and I get k over 2 times 25 minus k over 2 times 0 is equal to 3. And so that the 0 cancels out, and I am left with 25k over 2 is equal to 3. So k ends up being 6 over 25. Now that I've found my k, I can take this and do it stretching the spring from 25 centimeters to 30 centimeters. So to find how much it takes to stretch from 25 to 30, I'm going to do the definite integral from 5 to 10, 6 over 25 times x dx. And I already know that this will be, antiderivative here will be 6 over 25 times 1/2 x squared. So taking that, I have the 6 over 25 times 1/2 times 10 squared minus 6 over 25 times 1/2 times 5 squared. this will be the work done to stretch from 25 to 30. Now, a question here, or the key insight that we need, is to recognize that instead of 20 and 25, we're dealing with 0 to 5. And instead of 20 to 25, we're dealing with 0 to 5. And instead of 25 to 30, we're dealing with 5 to 10.